The divergence theorem says that the triple integral of the divergence operator of a vector field over a domain D is the same thing as the flux out of that domain. So let's return to the example we did at the beginning of this lecture, where we defined a domain as the region between the unit sphere and the sphere of radius 2. And we were studying there the vector field given in coordinates by -4yz, 4xz, and -3z. And here the units are velocity units, meters per second. So we previously calculated the flux out of this domain by individually looking at the two parts of the boundary of this domain and calculating the flux directly. Well, we can now apply the divergence theorem, which says that the flux out of this domain is the same thing as the triple integral of the divergence of this vector field throughout the domain. So here, what is the divergence? Well, it's -4yz differentiated with respect to x, which is 0, plus 4xz differentiated with respect to y, which is 0, plus -3z differentiated with respect to z, which is -3. So now we're looking at the triple integral of -3 throughout the domain D, dv, which is really the same thing as -3 multiplied by the volume of this region. And to calculate the volume, all we need to do is calculate the volume of the outer sphere and subtract the volume of the inner sphere, and then we multiply that quantity by -3 here. When we do the arithmetic, we end up with -28 pi meters cubed per second, which is exactly what we got previously, except by using the divergence theorem, we've simplified our calculation. Let's look at some more examples. Here, we're defining a domain D as the solid cone depicted in this figure. So here we're looking at the cone defined by the equation z equals root x squared plus y squared, capped off at z equals 1. So this is a solid domain, which means that we're looking at everything on the cone and inside of it that's on or beneath z equals 1. Now, if we wanted to calculate the flux of a vector field out of this region, we would have two flux integrals to calculate directly. We would have flux over the conical part of this region, and then flux over the top disk part of this region. So we could calculate those two flux integrals and add them together to calculate flux. Or we can try to use the divergence theorem. So here the vector field we're studying has coordinates xy, 2xz, and -2z squared. Again, here units are the velocity units. The divergence of this vector field is xy with respect to x, which is y, plus 2xz with respect to y, which is 0, plus -2z squared with respect to z, which is -4z. When we add everything up, we get y minus 4z. So according to the divergence theorem, we can calculate the flux out of this three-dimensional domain, which is notated symbolically as double integral over the boundary of the domain of f dotted with d vector s. Well, the divergence theorem says this is the same thing as the triple integral of the divergence of our vector field throughout this three-dimensional domain. So now we're taking the triple integral throughout this solid cone of y minus 4z dv. And to calculate this triple integral, we can either try a direct calculation or we can switch to a new coordinate system. I chose to switch to cylindrical coordinates here, where the region is described quite nicely. Z ranges from root x squared plus y squared, which is equal to r in cylindrical coordinates, up to z equals 1. And then r ranges from 0 to 1, and theta ranges from 0 to 2 pi. In cylindrical coordinates, y is equal to r times sine theta, and z is equal to z, so we're still integrating y minus 4z, which is r sine theta minus 4z. But since we've switched to cylindrical coordinates, we have to multiply by the Jacobian determinant, which is for cylindrical coordinates equal to r. And now we have a simple triple integral on our hands. And when I did the calculus, I ended up with negative pi meters cubed per second. Let's do one more example. Here we're defining D as a solid paraboloid depicted in this figure. So here we're looking at z equals 4 minus x squared minus y squared. So we're looking at an upside down paraboloid shifted up 4 units. And we're cutting the paraboloid off down here at z equals 0. The vector field in play is f equals negative 2yz negative y squared z. Again, units being velocity units. If we wanted to do a direct flux calculation here, we would have 3 parts of our boundary. We would have 2 parts of our boundary. We would have the paraboloid, which is described by z equals 4 minus x squared minus y squared. And then we would have this bottom disk part of our 3-dimensional solid. But since this is a 3-dimensional solid, to calculate flux, we can try to use the divergence theorem, which will first require us to calculate the divergence of our vector field, which is negative 2yz differentiated with respect to x, which is 0, plus negative y squared differentiated with respect to y, which is negative 2y, plus z differentiated with respect to z, which is equal to 1. So the divergence of our vector field is negative 2y plus 1. So now, according to the divergence theorem, the flux out of our 3-dimensional domain, again symbolically, is notated as double integral over the boundary of our domain of f dotted with d vector s. But the divergence theorem says this is the same thing as the triple integral throughout the region of the divergence, which we just calculated to be negative 2y plus 1 dv. And we can nicely write this region again in cylindrical coordinates. So here in cylindrical coordinates, z is ranging from 0 up to 4 minus x squared minus y squared. But in cylindrical coordinates, 4 minus x squared minus y squared is really 4 minus r squared. The radii throughout this region are ranging from 0 out to 2. And the angles in this region are ranging all the way from 0 to 2 pi. Now, negative 2y plus 1 in cylindrical coordinates is negative 2r sine theta plus 1. And since we are switching to cylindrical coordinates, we have to multiply by the Jacobian determinant, which again is equal to r for cylindrical coordinates. And then now we can evaluate our triple integral. And when I did the calculus, I got 8 pi meters cubed per second. So again, the divergence theorem has allowed us to take what would be a difficult direct calculation, because we would have to calculate flux here, we would need to parameterize the paraboloid part of this domain and then parameterize the disk part of this domain and solve 2 flux problems. But instead, we just need to calculate 1 triple integral of the divergence of our operator throughout this 3-dimensional region.